Thanks to TÜBİTAK for this great organization. Hello, I am Esref Erdogan. I am a master student at such university. Seminar location 6-point results for almost F-type contraction. Let's start. 6-point theory students in complex metric space started with Banach in 1922. The Banach contraction method principle not only guarantees the excess of the fixed point of the method, but also show the uniqueness of this fixed point and how it can fall. The theorem, which is considered to be best known result of fixed point theory, and the beginning of the theory is given by the famous Banach fixed point theorem in the following form. Let X be a complex metric space and X2X a contraction method with an ellipsis constant. In this case, D has a single fixed point Z in X. Moreover, for any X0 in X, the sequence converges to this fixed point of T. A number of efforts have been made to enter and generalize Banach contraction principle because it plays a fundamental role in metrical fixed point theory. Theorem: let X be a metric space and let T be a submetric on X. If there exists beta real number such that S and 1, then there has a unique fixed point. Theorem: let X be a metric space and let T be a submetric on X. If there exists gamma real number such that S and 2, then there has a unique fixed point. Let X be a complex metric space alpha, beta, gamma real numbers with f(x) from X a function such that for each company of different points xy in X, at least one of the following contribution is satisfied, then Fs unique fixed point. Let X be a complex metric space. The generalization decayed contraction submetric of X then has unique fixed point. On the other hand, one generalization of the Banach contraction principle is the Erdogan's theorem. Let X be a complex metric space. Let T X to X be a given metric such that S and 3 then has a unique fixed point in X. We have seen that the coefficients in the contraction we have given above. Now we will see that these coefficients or the sum of the coefficients will be 1 or the greater in the contraction we will give. This type of contraction was described by Berinda in 23. Let X be a metric space. AMF X to X is scalar with contraction if there exists a constant delta and some L such that S in 4. Due to symmetry of this time, the weak contraction condition for implies inverse the following dual 1, S and 5. Consequently, in order to check the weak contractivity of it is necessary to check the work 4 and 5. Example, T symmetric defined by delta and is an almost contraction for L. Also, the fixed point of this mapping are 0 and 1. Theorem. Let X be a complex metric space and X to X a weak contraction. That is, let delta and L be S in 6. In this case, they have a fixed point at X. It should be noted here that is the Banach fixed point theorem. The uniqueness of the fixed point was guaranteed. However, in almost contraction, as seen in the example above, the fixed point might not be unique. To answer this uniqueness, we can guarantee uniqueness by adding an addition requirement similar to almost contraction recurrent. Theorem. Let X be a complete metric space and X2X a weak contraction. That is, let delta and L be Sn in 7. In this case, there has a unique fixed point at X. The more remarkable generalization of the Banach contraction principle was given by Twardowski in 20 work by defining the concept of F contraction. In this generalization, Twardowski demonstrated that F contraction mapping in complex metric space have a single fixed point. Now let's first give the concept F contraction and some example of it. Then let's examine the fixed point theorem met with the help of the contraction. Let F be a matrix satisfying F1, F2, F3 contraction satisfying. A matrix X2X is said to be an F contraction if there exists so such that S in A. Let X be a complex metric space and let the X2X be an F contraction, then it has unique fixed point in X. In this paper, we modify the concept of F contraction matrix to orthogonal set and provide some fixed point theorems for almost F contraction matrix in orthogonal complete metric space. But first of all, let's remember some information about orthogonal metric space. Definition: let X be a non-empty set and third the binary relation defined on X. If binary relation third fulfills the following criteria: 9. Behind paper pair X third knows as an orthogonal set. The element X0 is scalar and orthogonal element. We denote this O set or orthogonal set by X verb. Example, let X define M third and if there exists K such that it is to see that 0 third and fourth and N, hence X third is an O set. Example, let X third be an orthogonal set any two elements XY in X such that X third Y, then X, Y in X are said to be orthogonal relative. A sequence Xn is scalar orthogonal sequence if Sn11. Similarly, a Cauchy sequence Xn said to be an orthogonal Cauchy sequence if similarly Sin11. Let X third be an orthogonal set and D be a metric on X. Then X third D is scalar and orthogonal metric space. Definition: let X third D be an orthogonal metric space, then X is said to be a complete if every Cauchy or sequence is converse in X. Let X third D be an orthogonal metric space of a function fx2x is said to be orthogonal continuous at X if for each or sequence Xn converging to X if place, or F is third continuous on X if F is F continuous at every X in X. Definition: let a pair X third be an O set where X be a non-empty set and third be a binary relation on set X. A mapping fx to X said to be third preserving whenever X third Y and directly third preserving if whenever X third Y. Theorem: let X be third be an O complex metric space and lambda, let fx2x be lambda continuous, lambda contraction, and lambda preserving. Then F has unique fixed point X. Theorem: Let X part be an all complex matrix space with an orthogonal element x0 and the x2, x satisfy the following condition 1, 2, 3. Then there has a fixed point. Moreover, if the fixed point of the is unique. In the section, we got a definition of generalized orthogonal almost type F contraction, and using the contraction, we obtain some result on a complex orthogonal matrix space. X per D. Definition: X per D be an orthogonal matrix space. A mapping T X to X cannot generalize orthogonal almost F contraction if there are F in F. And lambda such that the following condition holds. Sn 13, 14, 15 theorem that X per be an all complete orthogonal matrix space with an orthogonal element x0 and the matrix on X satisfy the following continuous one is for preserving there's and generalized orthogonal almost type F contraction. There's per continuous, then it has a fixed point in X. Looking at the proof x0 in xpn orthogonal element, it is shown that the sequence created with the orthogonal element s in 16 is an orthogonal sequence. In order to show that xn is a Cauchy or sequence, consider since x orthogonal complete, the axis is a point where xn converges in x, or the curve continues to extend over 5 x point is shown. Theorem that X per be an complete orthogonal matrix space with an orthogonal element x0 and the self-mapping on X satisfy the following condition. T is per preserving this and generalized orthogonal almost type F contraction. T is per continuous. Also to satisfy the following condition that exists F1 in F L1 greater or equal 0 at lambda such that Sn27. The hand has a unique fixed point X. Look at the proof for unique it assumes that it has two different fixed points and unique is object in the triangle. Hence, it has unique fixed point. Let X per be an complex orthogonal matrix space with an orthogonal element x0 and TBL self-mapping on X satisfy the following condition. One, there's per preserving there's an orthogonal almost a contraction such that there's third continuous and it has a fixed point in X. Let X be a complex matrix space and the X to X be a mapping such that for lambda Sn13 1 behind it has unique fixed point in X. Reference. Thank you for listening to me.
Okay, we thank to Professor Erdogan for his valuable presentation.
Thank you.
If there is any question or comment, please use the question and answer button. Let me check if there is. Okay, there seems no question or comment. So we thank again to Professor Erdogan.
Thank you.
Stop your screen sharing, please.